So we did the Legendre polynomial thing. We had the black line here was our fourth order polynomial, and we were trying to do Lagrange polynomials and approximate it with a second order polynomial or a parabola. And there's our red parabola that we got, and it didn't look good because the black line doesn't look like it's being approximated by the red line. All right, but remember that Legendre polynomials is only supposed to work from -1 to 1. So when we scan into that region, looking at these two graphs from -1 to 1, it does look pretty good, right? The red does approximate the black. Okay, so that tells us our technique works in that interval. So let's take this fourth order polynomial that goes from, our data goes from 1 to 5. Let's move it over and squish it down so it fits in the -1 to 1 interval in which we're working. All right, so we want to move our polynomial to the interval -1 to 1. Our data starts at 1 and goes to 5. So I want for our old x of 1, our first x, I want that to be a new x of -1. Our old x of 5, I want that to be a new x of 1. So I'm going to do a linear transformation, just squishing and moving over. So how do I figure out how to do that? Well, I'm going to just write down a line. New x is equal to some number a times old x plus b some number. I just got to figure out what a and b is. Well, I've got the first point and the last point. I want my new -1 to be given by my old x equal to 1. So when I plug in old x equal to 1 and new x equal to -1, I get this equation with a and b. Use the other point. When I plug in my old 5, my old x for 5, I want my new x to be 1. So here's two equations, two unknowns. I can solve that and get a equal to 1/2 and b equal to -1.5, -3/2. So here's how I can change old x's into new x's. And check it out, it works, right? Let's make x equal to 5, our old x equal to 5. 5 times 1/2, that's 2.5. 2.5 minus 1.5 is 1. That's what we want. So here's our polynomial that's on the interval in the old x's. So these x's here are old x's. I want to move it over to be new x's. These x's are old x's. If new x is equal to 1/2 old x minus 3/2, then old x is equal to 2 new x plus 3. I just solved this for old x. So this 2 new x plus 3 is what I want to sub in for all these old x's here. And now when I clean this up, let's simplify this. I'm going to this should be the same polynomial but squished and moved over. Let's just check it out. Let's graph it. All right, I don't want to see that right now. So I'm only interested from -1 to 1. So, because and we should go to, yeah, I forgot we're supposed to go up to 20. Okay, so here it is. This, you should be looking at this saying, oh, it doesn't change the y values, right? We just moved it over and squished it. Comparing that to this picture here. Remember, we're only going up to 5, so we don't see this dip down here. Let's look a little bit. So I wanted it to look like this picture, but you see this picture all the way from 0 to 6. So let me open the viewing window a little bit here. So let's just go up to 2 and back to -2. And now you're like more convinced that this is that original polynomial just transformed, shifted over. Okay, so this is f of nu x. Okay. In fact, let's take this here. Okay, so now let's go back to where we did our Legendre polynomial from the last video. These were the pieces that we used from the last video. So I'm going to just, out of laziness, copy them and paste them down here for efficiency. Okay, the only difference is I'm still using the 0th order polynomial 1, the 1st order Legendre polynomial x. I'm still using the same polynomials. They still have the, the size of 1 is still 2, well, root 2, but we square it. I just need these as new numbers. So I'm taking this polynomial, this is our new x's, and I'm replacing these pieces here with it. Because now I'm in the proper interval, the -1 to 1 interval. All right, these numbers will be different. These numbers are going to go into here where they were before. So let's evaluate this. Now, I'm just asking the machine to do it. You could, ask Wolfram Alpha to do it or whatever. We're just integrating that polynomial, subbing in the top minus subbing in the bottom. It's the inner product with functions. So this, let's get these values here. And finally do this integration. Okay, so now we've got that was the top of these fractions. The bottom stays the same because they're just, p sub I is just a Legendre polynomial. So that's the number I want for the top here. This is the number I want for the top here. So everything's the same except I'm, working with a shifted polynomial. So it's the inner product of our polynomial with the 0th order divided by the 0th order with the 0th order times the 0th order. Our polynomial with the 1st order with 1st order, 1st order. Our polynomial with the 2nd order, 2nd order, 2nd order, 2nd order. Let's clean this up now. But now this is in new x's. So if I graph this, it's going to look close to this. But I want to be in the other interval. So let's put it back. So these are all new x's. Let's go up to our transform here. New x's are equal to Well, this is what I want for this is what I want for change new x's back into old x's. So new x is equal to 1/2 old x. These are all new x's. So I'm replacing that new x and that new x. And now when I clean this up, now these are old x's, right? So this is going to be our simplified polynomial with the old x's, the original x's, the x's that we want, the x's that go from 1 to 5. So let's clean this up, tidy this up here.
Okay, dude. These are all done.
Okay, if we did everything right, if we graph this, let's graph it. And, okay, there it is graph, but we want to see it from, let's say, 0 to 6.
So any larger than drier now? What? This one. This one? Oh, that's one. Must be like 2 days.
There it is, from 0 to 6.
So any soft in there?
And we want to see our original polynomial. There's our original polynomial. Okay. Now you're not impressed because of this piece here, but keep in mind we're only trying to match from 1 to 5. So don't look here. It's pretty good. It's pretty good from 1 to 5. Can I change the color on that? Yeah. Let's make our parabola red like we did before. There. Man, okay. Be impressed from this region to this region. It did its job. We don't have any, we don't want to extrapolate. We don't have any data actually after 5. So our fourth order polynomial necessarily drops down, but that's just because we had 5 data points, got a fourth order polynomial. So a fourth order polynomial either both go up like this or both go down like that. So I'm happy with that. What's next? Okay, that's it for Legendre polynomials. Now you know how to get a approximate a polynomial with a smaller order polynomial. There's going to be a couple of homework questions in the problem set, but first there's some stuff for you to try with, try it and then see if you match the answers. Okay, the last thing I want to do is I actually don't want to do it because where is it here? Cubic splines. I don't like them. I don't like them. This is another way to approximate a curve. A cubic spline, all a cubic spline does is fits a cubic in between 2 points. So if we have a series of points, cubic splines are going to fit a cubic in between the 2 points, and it's going to use a different cubic for each pair of points. It seems really cheap to me. It's a technique. I think it's a bad technique for us in finance. It makes the curve look good, but I think you're hiding any meaning. It's not useful for interpolating between the points. So I'm not going to go into it much. I'm just going to say that it's a thing that people do. Cubic splines, you have a bunch of points and it just makes a different cubic joining the points. It makes the cubic, okay, why is it a cubic? If I have one point, this point it's attached to this interval and it's attached to this interval. We want the y values to match at the two splines, so that's one equation, one unknown. We want the slopes to be smooth, so it's not sharp pointed, so the derivatives have to match. That's two equations. We also want the second derivative to match, so that's like three equations. If we do that, if the second derivative and the first derivative match at each one of the points, and the y values match at the points, that'll give us so many equations, so many unknowns. We're going to miss a couple of unknowns, so we just, because at the end points we don't have the last point and the first point. The last point and the first point, we don't have any slope to match it with, so we just say that the second derivative, the concavity, has to be 0 at the beginning point and at the end point, and that gives us all the equations we need to solve for all the unknowns. You would never do this by hand. You would just ask the machine, give me the cubic splines. It would chug out and solve for the system of linear equations. The only reason I'm even mentioning it is so that if someone says, oh, why don't you do cubic splines, you can know what they're talking about. And I think the answer would be, it's not a real good technique. It's kind of a cheap, cheesy thing. You might as well just connect them with straight lines. That's easier and only mildly not as good.